Hello all, welcome to this class on finite element analysis, and in this class let's solve this problem, that is determine the nodal displacement, stresses and each elements and reaction of the supports for the stepped bar. And in this problem you have a stepped bar, you have four stepped bars actually. So you have four elements basically. So this is element 1, 2, 3 and 4. So let's see the given data. So here diameter is given for every element or every bar. So it is for this first element, it's made up of steel and it is given as 60 mm. The second element is made up of Cu. Cu is nothing but copper and the diameter is given as 40 mm. And third element is Al. Al means aluminium. It is 30 mm. And fourth element is made up of brass and the diameter of that is given to be 20 mm. And the lengths of each element are 900, 800, 700 mm and 600 mm. And you can see at node 2, 100 kilonewton force is acting in the opposite direction, and in node 3, 100 kilonewton force is acting in the opposite direction, and at node 4, 50 kilonewton force is acting. And this X indicates displacement is towards this right direction. Therefore, this force at nodes 2 or nodes 3, we have to consider it as negative. Okay, because it is opposite to the direction of the displacement. So now let's and also the Young's modulus of all the elements are given. So Young's modulus of copper, that is element 2, it's given as 100 GPa. Young's modulus of steel, that is element number 1, that is given as 200 GPa. Young's modulus of aluminium, third element, 70 GPa. Young's modulus of brass, fourth element, is given as 70 GPa. Now let's try to write the given data. So L1, L2, L3, L4 is given directly over here. There is no, there is no need of any confusions over there, I guess. A1, see, this is a bar of circular cross section, therefore A1 will be pi by 4 d1 square. So pi by 4 d1 square, in the sense pi by 4 d1, d1 is 60 square. The answer is found to be 2827.43 mm square, and I have highlighted that answer. And A2 is also the same case, pi by 4 into d2 square, d2 is found to be 40 mm, and the answer is found to be 1256.64 mm square. So you can just put it in calculus and you will get the answers for this. And A3 is pi by 4 30 square, 706.86 mm square, I'm getting the answer as. And A4, pi by 4 into 20 square, 314.16 mm square. And similarly E1, E2, E3, E4, let me write Young's modulus of elements 1, 2, 3 and 4. So steel is first element, and copper is second element, aluminium is third element, and brass is fourth element. And the respective Young's modulus are 200 GPa, 100 GPa, 70 GPa and 70 GPa. When it is converted into Newton per mm square, this is found to be 2 into 10 to the power of 5, and this is 1 into 10 to the power of 5, and these both are 0.7 into 10 to the power of 5. And these conversions I have just taught it in video number 1. If you want, you can just see that video to understand, to have a better understanding. And force at node 1 and node 5 will be equal to 0 because the nodes are fixed. So therefore the force acting at the respective nodes will be considered as 0. And at F2 and F3, the 100 kilonewton force is acting in the opposite direction. Therefore we can consider it as negative. And at F4, 50 kilonewton force is acting in the positive direction. The first thing what you have to draw is the step number 1 is the FEA model. So let me try to draw the FEA model. Here it is a 5-noded element. Therefore here let me just draw node number 1. So this is node number 2, and node number 2, let me just draw over here. And roughly let's try to assume the distances as a little bit like decreasing from each element, because it's 900, 800, 700 and then 600. So let me try to write it roughly a little bit smaller. So 4, and let me just write this as 5. So you can just see this is element number 1, this is element number 2, this is element number 3, this is element number 4. So therefore you have totally 4 elements, and the length of element number 1, L1, is nothing but 900 mm, and the length of element number 2, L2, is 800 mm. The length of element number 3, L3, is 700 mm, and the length of element number 4, L4, is 600 mm. So it is found to be so much, and you can just say at every node there is a displacement Q1, Q2, Q3, Q4 and Q5. So there is displacement as well as at every node, and at every node let me even indicate the forces. F1 and F2 and F3 are already shown it to be opposite F2, and here it will be F3 and F4 and F5. So this is nothing but the FEA model. The construction of FEA model is completed over here. So the next step, whatever we have to do is calculation of elemental stiffness matrix. So that is nothing but calculation of elemental stiffness matrix. I have already written and kept it over readily here. So that just we have to just substitute this K1 equal to A1 E1 by L1, 1 minus 1 minus 1 and 1. So area A1 is 2827.43, E1 is 2 into 10 to the power of 5, L1 is 900. So upon calculation, so let's see what do we get upon calculation. Upon calculation, we get 2827.43 into 2 into 10 to the power of 5. Okay, let me just leave out 10 to the power of 5. Only let's try to calculate only these numbers. So because 10 to the power of 5, it's common over every here. So in every elemental stiffness matrix. So let me just keep it as it is. So 2827.43 multiplied by 2 divided by 900. So that is found to be 6.283. So 6.283 will be multiplied inside and 10 to the power of 5 will be written over here. 6.283 minus 6.283 minus 6.283 and 6.283. So this is nothing but elemental matrix K1. So similarly, you have to just substitute all these values for K2, K3 and K4. So upon substitution, what the answers what do we get is, okay, you can just see I have just calculated for all the stiffness matrices. So upon simplification of all these numbers, except you can just leave this 10 to the power of 5, so that you will get this for the second stiffness matrix, you will get it as 1.5708. So that 1.5708 you can multiply it inside. Similarly for K3 you are getting 0.70686, and that K3 you can multiply it inside this 1 minus 1 minus 1 1, you are getting it like this. Similarly for K4, upon simplification of this number, you can just leave just the 10 power 5 and you will get this. If you want a detailed explanation, you can just watch my first video so that you will get a detailed explanation there. Okay, now next thing we have to do this global stiffness matrix. Global stiffness matrix is nothing but K equal to K1 plus K2 plus K3 plus K4. I have just written over here, that is you can just see clearly over here, that is I have just written over that K1, K2, K3, K4. So first thing at 1 and 1 we have only here, we don't have anywhere 1 and 1. So 1 and 1 we find 6.283, so it's nothing but 6.283. Next it's a 2 and 1. 2 and 1 we find minus 6.283. Next 3 and 1. 3 and 1 we don't have it anywhere. You can just see clearly there is no anywhere. Similarly 4 and 1 also we don't have it anywhere. Similarly 5 and 1 also we don't have it anywhere. Next 1 and 2. 1 and 2 we find it here. It is nothing but find to be minus 6.283. Next 2 and 2. 2 and 2 we find it here as well as here. 6.283 plus 1.5708. So let me just try to add that. 6.283 plus 1.5708. The answer is found to be 7.8538. 7.8538. Next it's at 3 and 2. At 3 and 2 you find it clearly, it's minus 1.5708. So next it's at 4 and 2. 4 and 2 there is nothing, nowhere connection is there. 5 and 2 also nowhere connection is there. Okay, now next is 1 and 3. 1 and 3 nowhere it's connected, 0. 2 and 3. 2 and 3 are connected over here. So 2 and 3 is minus 1.5708. Next 3 and 3. 3 and 3 are connected in two places. One is in second element matrix and third elemental stiffness matrix. So it is nothing but found to be 3 and 3 is connected over here. Therefore you will get 1.5708. Next 3 and 3 is also here. So therefore plus 0.7070686. So you will get it as 2.27766. 2.27766. Okay. Next 4 and 3. Are 4 and 3 connected? Yes, it's connected over here. So the answer is minus 0.70686. Next 5 and 3. 5 and 3 are connected nowhere. So it will be 0. 1 and 4. 1 and 4. 1 and 4 are not connected it anywhere. So you can just put 0. And similarly 2 and 4. 2 and 4 also not connected anywhere. It's 0. 3 and 4. 3 and 4 are connected over here. It is found to be minus 0.70686. Next 4 and 4. 4 and 4 is connected over here as well as here. So therefore the answer will be 0.70686 plus 0.366 0.36652. So the answer is 1.07338. 1.07338. And similarly 5 and 4, 5 and 4 are connected over here, so the answer is minus 0.36652. And next 1 and 5, 1 and 5 are nowhere connected, 2 and 5 are also nowhere connected, 3 and 5, 3 and 5 are also nowhere connected, while 4 and 5, 4 and 5 are connected over here. The answer is found to be minus 0.36652. And 5 and 5, 5 and 5 is connected over here, minus 0.36652. So these are all the answers whatever we have got. So the next thing what we have to do is, now we have to just substitute all those over here. So let me just try to write this matrix over here, this Q and this F. So this Q is nothing but global nodal displacement vector, Q1, Q2, Q3, Q4 and Q5. And similarly F1, F2, F3, F4 and F5. So in nodes 1 and 5 it's fixed, so 0, F2, F3, F4 are written. So let me just let me try to write it over here, this one. Okay, I've just written over this K, Q and F. So according to this problem, so next step will be like applying boundary conditions. So we have to apply the boundary conditions. So before applying the boundary conditions, we have to do one thing, that is we have to eliminate the row and column. We all know according to this problem, the first node and fifth node is fixed. Therefore, eliminate first row and first column and fifth row and fifth column. So let's try to, and before that, we have to even retain this 10 power 5. So see that you don't try to forget that, writing the 10 power 5. As I told, this 10 power 5 is common everywhere. So you can easily maintain that same 10 power 5, and see that even if it is not common, you have to make it common. That is very, very important. So 10 power 5 is written over here. I'll just retain it here as well. So here I have to eliminate the first row. First row throughout I'm going to eliminate, and first column I'm going to eliminate, and for fifth row I'm going to eliminate it throughout, and fifth column I'm going to eliminate this. So whatever the remaining, I'm going to write it now. So remaining I'm going to write it, and I'm going to find out the values of Q2, Q3 and Q4. I have just let me try to write all these remaining elements over there. So in that applying boundary condition, so I have just written it over here. So now we have to do the matrix multiplication. The order of this matrix is 3 cross 3, and the order of this matrix is 3 cross 1. The number of columns in this matrix is equal to number of rows in this matrix. And now let me just try to do the matrix multiplication. So first element multiply first element, second element, third element and third element. So I'll get the equation number 1, 7.8538 Q2 minus 1.5708 Q3 and plus 0 Q4, that is equal to minus 100 into 10 raised to 3. So that's what I'm going to get in equation number 1. Second one, I'm going to multiply this row with this column. First, second element, third and third element. So minus 1.5708 Q2 plus 2.27766 Q3 minus 0.70686 Q3, sorry Q4, that is equal to minus 100 into 10 raised to 3. And similarly, and the 10 power 5, please don't forget that. So 10 power 5 has to be there. Therefore, if 10 power 5 is there, 10 power 5 is going to be here. And similarly, here and here 10 power 5 is going to remain. And finally, it's going to be 0 into Q2 minus 0.70686 Q3 plus 1.07338 Q4. So 10 power 5, that is nothing but equal to 50 into 10 raised to 3. So this is what we have got. Now upon same thing, you have to just go to mode, which I have done it in video number 1. If you want, you can check it over there. You have to just go to mode, equation, number of unknowns are going to be 3 this time. This is going to be A1, A2, A1, B1, C1 and D1. So that's what it's going to be. So upon calculation, the answers whatever we are going to write are Q2, Q3, Q4 equal to, okay, now I have substituted all the values, like this is A1, this is B1, this is C1 and this is D1. Similarly A2, B2, C2, D2, A3, B3, C3 and D3. And with the resulting answer, you have to divide it with 10 power 5. So you're getting X is nothing but Q2. I'm just getting it as minus 24,358.319. I'll just round it off to 32 divided by 10 power 5, because that we have to divide it with 10 power 5. Similarly Q3 I'm getting it as I'm just getting that as minus 58 126.6667. I'll just round it off and divide by 10 power 5. And similarly Q4, so let me just calculate and write those answers. Q4, it's nothing but Z is nothing but 8303.28 or 29. Let me just round it off to 2.9. So divided by 10 power 5. So now let me just try to reset this. So upon that we'll try to calculate this minus 24,358.32 divided by 10 raised to 5. So the at Q2 or that node 2 the displacement is found to be 0.2436 mm. So I've just rounded off this value, so it's found to be so much. And at Q3 the answer is found to be 58,126.67 divided by 10 raised to 5. So the answer is found to be minus 0.5813 mm. So I've just rounded off the value. So similarly Q4 will be 8303.29 divided by 10 raised to 5. So the answer is found to be 0.083 mm. So now I've got Q2, Q3 and Q4 values. The next step what I'm going to do is stresses in each element. So stresses in each element have to be found. There are totally 4 elements. So sigma 1, sigma 2, sigma 3 and sigma 4 is what I have to find out. So stress 1 is the formula will be E1 divided by L1 minus 1 and 1, and it will be Q1 Q2 over here, Q1 Q2. And E1 is nothing but found to be, so E1 is 2 into 10 to the power of 5, 2 into 10 raised to 5 divided by L1 is 900, so L1 is 900 and minus 1 Q1 is 0 and Q2 is we have found it already, so that is nothing but so much. So let me just try to put this value into the calculator. So 2 into 10 to the power of 5 divided by 900. So the answer is 222.22. So 222.22. So let me just multiply the 222.22 inside, minus 222.22 and plus 222.22. So that one, let me just try to multiply over here with this. So the answer will be like here you have to do matrix multiplication. First element into this, second element into this. First element multiplied by 0 will be 0. Second element multiplied by that, it will be sigma 1 equal to 222.22 multiplied by 0.2436. The negative sign of this I'll just write it at the beginning. So therefore the final answer will be 0.2436. So 0.2436. So the final answer will be sigma 1 equal to 54.13 Newton per mm square. So that is found to be the final answer. So similarly you have to find out, so let us just return it over here, sigma 1 equal to 554.13 Newton per mm square. Similarly we have to find it for element 2, element 3 and element 4. Similarly, if you just look at for this second element, I've just substituted it over there. Sigma 2 equal to E2 by L2 minus 1 Q2 Q3. So I've just substituted all the values. So first let me just find out this value. That value is nothing but found to be 10 to the power of 5 divided by 800. So the answer is found to be 125. So let me just try to substitute that, multiply that 125 inside. I'll get like this, and it is going to be, so let me just try to apply the matrix multiplication. So I'll just get it minus 125. That's first element into first element over here, second element into second multiple. So minus 125 into minus 0.2436 plus 125 into 0.5813. So when I just do it, I'll guess the answer as so 125 into 0. So minus into minus will be plus over there. So I'm just going to get it here, 30.45 plus for this 125 plus into 0.5813. So like 30.45 plus. So I'm just getting the answer as 103.1125. So that is nothing but the stress in element 2. The answer SI unit will be Newton per mm square. So similarly, let's try to find out for this as well. So when I just try to divide this value, so just try to, when I simplify that, I'll get 0.7 into 10 raised to 5 divided by 700. So it is nothing but 100 exactly. So minus 100, and this is going to be same. I'm just going to write it as ditto. So minus 100 into first element, this first element, and 100 into second element. Minus 100 into minus 0.5813 plus 100 into 0.083. So it is found to be, so minus into minus it will be plus. So therefore 100 into 0.5813 plus again 100 into 0.083. The answer is found to be 66.43. So therefore sigma 3 or stress in element 3 is found to be 66.43 Newton per mm square. So I'm just doing matrix multiplication only over here. So next, let me just try to simplify. So this one I'm just going to multiply with this one. So I think you're understanding that. Even here also I'm just doing matrix multiplication only. So let me just do for the final element. So final element 0.7 into 10 raised to 5 divided by 600. So the 0.7 into 10 raised to 5 divided by 600. So it is found to be 116.67. So 116.67, let me multiply it inside, I'll get like this, and 116.67, and the other one will be, other matrix will be 0.083 and 0. So upon matrix multiplication, when I just multiply it, first element into this, second element into this, second element into the 0 will be 0, first element will be like 116.67 multiplied by 0.083. The answer is found to be, so minus 116.67 into 0.083. The answer is found to be minus 9.68 Newton per mm square. So we have found out stresses in all the elements, sigma 1, sigma 2, sigma 3 and sigma 4. The next thing what we have to do is to find out the reaction of the supports. The reaction of the supports are nothing but at nodes 1 and 5. So next, let's try to solve this step number, the last step, reaction at the supports. So reaction at the supports. So supports are at the nodes 1 and 5. So only for nodes 1 and 5 we have to find out the reactions. That is, the formula will be K into Q minus F. So that is R equal to K into Q minus F. I have just written the big global stiffness matrix, and the global load displacement vector is also written over here, and F is also written over here. So K into Q equal to F. So I don't have to solve the complete matrix multiplication. I'll not be solving. This is the order 5 cross 5. This is the order 5 cross 1. Only this first row and first column and fifth row and fifth column. Only that I'm going to do, because only for R1 and R5 I'm going to find out. So only if I do that, that will be fine. So first row, and I'm doing 6.283 into 0 minus 6.2 into this one. So like this, third element into third element, fourth element into fourth, fifth into fifth. Like that is what I'm going to do. So R1 equal to 6.283 multiplied by 0 and minus 6.283 into again minus 0.2436, and third, fourth, fifth elements you have 0, 0 and 0. So multiplied by that, will this would be 0 again. I don't have to write it also. So minus 0, minus multiply that with 0. So therefore even this is also going to be 0. So minus into minus, I'll get it plus over here. So 6.283 multiplied by 0.2436. So the answer is going to be 1.5305. So therefore R1 equal to 1.5305 newtons. So that is nothing but going to be the, and sorry, multiply that with 10 power 5, because 10 power 5 is going to be here. So R1 is nothing but 1.5305 multiplied by 10 power 5, that has the newtons. Now R5. R5, already you have 3 zeros over there. So 3 zeros multiplied with this first 3 elements will yield 0. And also fifth element multiplied with this will be 0. Only fourth element I'm going to multiply it minus 0.36652. And that I'm going to multiply with 10 power 5. And that with this 0.083, and that answer I'm going to subtract with this fourth element over here. So fourth element is 50 into 10 raised to 3. So when I'm just trying to do that, I'm going to get it as, so let me just try to 0.36652 multiplied by 10 raised to 5, that multiplied by 0.083. So the answer is found to be minus 3042.116 minus, so let me just put 15 into 10 to the power of 3. So the answer is found to be minus 5342.116. So that is nothing but R5. So we have just found out R1, R2, like R1 and R5, and we also found out stresses in each elements. We have just found out all the nodal displacements. I hope you have understood this problem. Thank you.